try to do my best. The first part, I'm going to talk about learning structures using large-scale models and architecture. This is a little bit like a Pink Floyd album. That is part 1. Then I'm going to talk about the sawtooth method. This is a teaching method that we use here at Yaşar for integrating seismic design principles into architecture. Then I'm going to continue with the learning structures using these large-scale models, the second part. And because this is about current debate, I should introduce contemporary approach. And I felt that talking about the Pompidou Center, which is a work that I respect very much, is not necessarily talking about contemporary architecture. I found an example that was just finished in Cambridge, and I would like to show you a video of that building as a matter of example to kind of summarize all the things I'm going to say. So these are the contexts. I'll try to go faster so we are able to visit them all, but at the same time, I'll try to go in at a speed that we can actually debate if you want. So please, again, if you want to ask something, just interrupt me or open your microphone and ask me the question. The first thing I'm going to say, and these are part of the thought I've been having since a long time ago, is that a building construction system is not the same as a structural system. And this is in my opinion, very common misconception or misunderstanding. And in order to explain what do I mean with this, that these are not the same, I'm going to use as an example a simple brick wall. And I'm not going to even show an image because my guess is all of you have a perception of what is a wall and what is a wall made out of bricks. So from the building construction perspective, a brick wall requires a knowledge or an understanding of the source material, which in this case is a brick. It also entails a system of production or a system of fabrication. It explains how these basic elements are going to be connected. It explains how they are going to be connected, how they are going to be merged with each other using the mortar, and also explains some techniques depending on what is the goal, what is the type of masonry, brick masonry you would like to build. So all this, let's say, body of knowledge is what we call building construction. However, as a structural system, a brick wall might or might not transfer loads. So it might be subjected to forces. When we talk about the brick as building construction, we don't talk about forces. We don't talk about structural, non-structural elements. We talk about, again, source materials, manufacturing processes, building or fabrication processes again. But in a structural system, we start talking or we start looking at this wall as its role in transferring loading. So we can say, we start talking about things like, okay, it's a structural wall if it's connected to the reinforced concrete frame, or might be non-structural if these bricks are not connected to the frame. And as such, this wall is subjected to damage. It might have damage because the load exceeds the capacity of the wall, or simply, which is the same, for example, like in this picture, it might be affected by an earthquake. Now, from the design perspective, in brick, a wall which is made out of brick can be left to express its own materiality or its own tectonics by leaving it exposed, like in this picture. And we can create some variation, some rhythm in the facade by moving things off plane, out of the plane. So we have this kind of dynamic facade, and all of this is made under the consideration of the things we were talking before, that these are made by tiny elements called bricks that need to be assembled in a sequence, which is based on a certain order. And at the same time, these are going to be structural elements because they are going to be transfer load. So the design organizes uses this knowledge to create architecture. Or we can take this material and just cover it and just painted it, and then the material disappears and becomes something else. That is something we designers do. And there is in my opinion, and this lecture is about this, there is a higher level when you combine these three body of knowledge. Well, architecture is actually a discipline. You combine the knowledge of knowing how you can assemble these elements. You combine the knowledge of understanding how the system is going to transfer loads, and then you put all this knowledge in the pursuit of a higher design idea. So you ended up with things like this one, which is a church in Uruguay in South America, designed by Eladio Dieste, who was an engineer and a builder. This church
Excuse me, Hojam.
is...
Hojam, I cannot see your screen. I can only see the first picture in which it's written Warren Truss, and it's stuck in my screen. I can only see the first slide of your presentation.
Ah,
Does anybody else have this problem?
Can follow all the slides.
can you see the church?
Yes.
Yes.
Ah, okay.
Yes.
Okay,
Ryan, get out of log out, log in again. Sometimes it just gets stuck.
Oh, okay, Hojam. I'll do that.
Right.
Thank you.
Okay.
Thank you for letting me know. Anyways, and again, if there is any problem, please inform me. So the point I was trying to make is, in this church, is not only the tectonic of the material what is creating these piece of architecture, is also the understanding of what is the best way that we can create a wall that is self-supporting. So this is a ruled surface, and here at the bottom there is a straight line. So all the walls start as a straight line, and then in the upper part there is a curve that is going around here. So the wall starts straight and then opens in this way, which makes the entire wall quite stable in combination with these vaults, and then again it's symmetrical, so the system is in balance. So here is the ultimate combination of this three body of knowledge. So I'm going to now start the presentation properly. So, and I'm going to explain, I'm going to go in some sort of chronological way to explain some of the subjects that have interest me from my early years as instructor, related with teaching structures and teaching building construction, although my interest and my expertise went into structure and architecture rather than building construction. So in the first years, when I was asked to take two courses, one was building construction in reinforced concrete, which is in the image you see to the left, and the other course was structures in nature. Now, these two courses were, when I received them, when I got the responsibility to teach them, they were there. I mean, they had some sort of tradition. It's not that they started with me. And I'm talking, by the way, back in Chile, in my country, I started to teach in the same university I graduated from in architecture, and this course about concrete was much more based on, I would say, technical knowledge. So you receive in that course knowledge about how to make mixtures in concrete, how much water should you put, how much sand should you put, and what type of concrete you're going to receive, how much strength, the time you need for the concrete to cure, and so on and so forth, technical knowledge. And this other course, which is called Structures in Nature, which I also undertook when I was a student, was much more based on models. and it was very much experimental, and it didn't have any theoretical framework. We were not really studying anything. We were just making models. So, for example, the assignment was, okay, take an orange, cut the orange, and then try to understand the structure inside, and then make a model out of it. That was the type of assignments we were doing. So we were having a lot of fun in these structures in nature because we were making models. Like in this image, you are seeing a model that I guide as an instructor, which it was about elasticity. So the students tried to make some sort of adaptive / kinetic structure that was able to expand and then come back to the same position, being at the same time able to support some load. So this was more or less the courses as they were. And then I started to think why we need to keep one course with a lot of technical knowledge and the other course in an experimental way. What happened if we start combining this? Because I realized, of course, that the students were really sleeping when we were talking about concrete, and then they were much awake and much more interested when we were talking about these models. But at the same time, I felt that we need these two fields to be combined. So in the next year, I gradually start making models, introducing models in the course about concrete. So the students start putting their hands on and start making stuff. And of course, was still very much, let's say, constrained by the objectives and by the subjects of the course. But I noticed the students, in my opinion, were much more interested, and they started to remember better and connect this very abstract knowledge of, strength and stress with practical architecture. And on the other hand, the picture that you see to the right is students working with geometrical forms made out of cardboard, which was an attempt to introduce geometrical principles in these structures in nature. So we kind of first developed a kind of geometrical pattern, and then they were fooling around. They were literally fooling around with this to create some exercises on the spot during the class, and that's what they are doing. So then after that, I started to think that actually there were two types of models. One type of model that is building construction model, and the other one is a structural model. And both of them explain how. The difference is a building construction model is going to explain how building elements are organized to configure architecture, whereas a structural model is actually explaining how structural elements are going to organize in a way that they can transfer loads. So both of them are systems because they are composed of elements, but these elements are different in nature and they are organized with a different purpose. And so I decided that I would like to concentrate more in structural models, because if I concentrate in structural models, they can understand the logic of how and which type of elements are concentrated. But in order to introduce the building construction knowledge, I will make them build these models. In my opinion and my approach, that is the way they will learn both. Now, there was another issue here that is very important, and it has to do with structures. A structure at the end, it's a system which is composed of elements that are organized to transfer loads. And the most basic load, and the type of load that you will never can escape from, is the one that is produced by gravity. The acceleration of gravity, which is almost 10 meters sorry, per second. So what is the effect of the gravity on built objects? Imagine that we have this cube whose dimension is L, and imagine that this cube is going to be made out of material whose density is around 1 ton per cubic meter. So I'm going to call this cube A, and I'm going to give a dimension of 1 meter. Of course, the mass is going to be 1 ton, which is the result of multiplying the volume, which is 1 cubic meter, per the, times the density, which is 1 ton over cubic meter. So that is 1 ton. So let's suppose now I'm going to increase, make it bigger, this cube 2 times. So I'm going to call this cube QB, and of course the dimension now is going to be 2 meters. If I want to calculate what is the mass of this new cube, I'm going to realize that now the mass is 8 tons. So you would say, well, wait, you increase the dimensions twice, but the mass went from 1 ton to 8 tons. So how that is explained? Because when you increase the size of something, the gravity is going to affect that to the cube of that proportion. And that is a very old principle that was first enunciated, or at least history tells that it was Gauss' square cube law. And basically, again, it means that if you change the dimension, if you increase the dimension of an object linearly, its mass is going to increase exponentially, not linear. And that is very important because when you start making large models, when you start making big things, the gravity start becoming more and more a problem for you. And that was my goal. So we start making big models. I mean, when I say we, I'm actually saying the students. I didn't do any of the models you're going to see here. I start forcing them to make big models. Again, because behind these big models, they had to deal with the problem of the gravity, the problem of making them stand, but at the same time, they have to deal with the problem of fabricating them, which brought them the knowledge of building construction. So we, again, as if you remember, I showed you before on high part shell, we start doing the same high part shell now bigger, and we were using glass fiber here. And you can see to the right, there are these, how we call it, some sort of framework to create these wire welded high parts. And as I said, we were using actual gravity. We were using actual load to create this type of exercise. To the left, you see a very well-known principle, which is called hanging change, which implies that the form that these elements are going to take depends on the loading. So depending on where you're going to put the loads, you are going to obtain these shapes. And for obvious reason, all these elements are acting in pure tension. We were using sandbags here to create this form. Later, the students applied plaster here, and then they let it dry. And then what you see to the right, you see that they turn this model upside down, and now the whole structure is working under pure compression, and which is, by the way, the symbol of La Sagrada Familia, which is a church it's a cathedral actually in Barcelona in Spain. And this principle was exploited and was not discovered, but was exploited very much in architecture by Antoni Gaudi. This is a work, making a model of the first church I showed at the beginning. Remember the one that Chayan couldn't see, the one with the brick, the Church of Atlantida in Uruguay. They are making a model of it in reinforced concrete, because we were also exploring, we were saying, okay, what if we change the material? What's going to happen? And by the way, this is one of my favorite pictures ever about my experience as instructor, because I took this picture, of course, from upper floor, but is to me is the synthesis of teamwork, which is something that it was always necessary in this exercise. This exercise, these models you're seeing are huge, and they're always made in 4 weeks, and not full 4 weeks, because they, like you, they were taking other courses and they were having studios and so on and so forth. So it was a very intense workload. And this is the model, of course, exploring membranes about a stadium, I think, in Saudi Arabia. I am not really sure, and I'm sorry if someone knows this project and knows exactly what it is. but it's a structure made out of elastic membrane, so they made the model in the same way. And the colors is not something, let's say, related with design. It's simply that they run out of this elastic fabric. We made some, let's say, classics shell works. In this case is the work from Eduardo Torroja. It's a cantilever shell. So these guys made it in reinforced concrete. And then at this point, we started to think maybe, because, okay, we made the models. This is the model you see there, but then we have to demolish them. We couldn't leave that huge piece of concrete there in the middle of the courtyard. So the guys I realized the guys were having a lot of fun when they have to demolish. I think it's a kind of catharsis, like you spend so much time, so much energy building something, and now you can destroy it. So they were having fun, hammering down. And this is the picture to the right. So then I thought maybe we should include this destroying the model as with a certain pedagogic outcome or goal. So we start testing. We said, okay, we're going to make models and we're going to test them. So this team was studying the Hagia Sophia here in Turkey, in Istanbul. So they decided to study the dome. So in order to have a background, a framework, actually, they make this perfect dome, and then they use a thickness of 50 millimeters, which is what appears here at the bottom. And then they start putting this, they put this block here. It's a concrete block. It's for testing reinforced concrete capacity, the strength, this one. And it weighs around 8 kilograms, okay? Just keep that in mind. And then they put one with the hope that after 2 or 3, this thing will break and we will understand how much it works. But they put a lot of blocks and still nothing. And they put all the blocks they could find in the campus, and still the thing was too strong. And so then we said, well, we cannot really destroy this thing, so maybe we are using too much material, so we should do it again in a thinner version. So in this case, we use the same form, but we use a thickness of 8 millimeters. But the guys didn't want to go again all over the experiment, putting block after block. So they just start pushing it down until they broke it. And we realized, okay, now this is breakable. So then after that, we went for the real Hagia Sophia dome, which has this perforation at each side, and then we start loading it again, and then we found out what is the ultimate strength and how it breaks. So we also add this experience to testing the models to understand how these things can work, and for example, how these openings can be reinforced in such a way that still the system can resist, can work as a structural system. And gradually, I mean, during all these years, all the exercise I'm showing you is the working process of around 4 years, 4 or 5 years, with different students in the same class. We all started to realize that there was a huge learning process involved in this, not only in terms of construction, but also in terms of designing these. I asked them to one team to recreate this arch. It's a catenary arch, and I think it's a real work. I think it's in the United States somewhere. So then the picture that is to the right, the students are using the hanging chain principle, which is they have a rope and then they have weight distributed to equal distance. So then you're going to create a catenary funicular curve. And then they were asking me like how do we do this? And I said, oh, just draw the curve. And then after the picture was taken, we were drawing the curve, and that is what we used to create the model. And so we started to realize that the key to build these things was always different. There is always a process of learning involved, not only in the structural part, but also in the construction part. So if in the funicular, the key was understanding how you create the overall geometry, for example, in a tensegrity tower like this one, you will realize very soon, the students realize very soon, that the problem is not the overall geometry. The problem is not to understand how this system works, because after you get it, which you can get it in 10 minutes, and it's basically a tensegrity, it's basically a network of tensile elements, which means all the cables are connected to each other, but the compression elements, namely the bars, are all floating. They are not connecting to each other, and that is the tensegrity principle. And after you get it, after a while, you think, oh, that's very straightforward. It's not really complicated. The problem for building this is in the connections. How you create the proper tension in order to keep it in the shape you want. So the students quickly realize that, and they learn how to solve it. So we, again, started to realize that actually these teaching structures was not about me giving knowledge to them, was all of us learning by doing. So that's why I start saying I'm teaching structure. I'm always say I'm learning structures with the students making models. So I'm going to finish this first part by explaining the process, the full process, in a few slides of one of these exercises that I was showing before, which is the Geodesic Dome by Buckminster Fuller. This is the problem. That slide to the left is the problem I gave to the students. I said you have to build a scaled down model of that. That was the brief. So then they found this very old drawing, they printed a larger scale, and then they start thinking, how do we do this? So again, they had to understand, and they realized that there is a geometrical principle behind these domes, which seems to be quite straightforward, but they realized that actually there were 5 types of triangles, like you can see at the bottom of this slide that is in the inside, right? Is left inside. And those type of triangles are going to create different geometrical patterns, which at the end can create the necessary curvature to create the dome. And then there are these students making the proper calculations, and all this was manual. There was no computer involved. There was no computational model. Everything was done by hand. And then again, they made a model, simplified model, with this, in this case, mathematical, geometrical knowledge to understand the different patterns. And with those patterns, they start building it up. Then they start the process of assembly. You know, there was a lot of cutting there, a lot of assembling, and a lot of marking, and they use a lot of colors, which unfortunately I don't have a picture of, to understand which part was going where. And this is the final result. Is the geodesic dome, of course, simplified version of the geodesic dome made completely out of timber bars. And if you look carefully at the dome, you're going to see here in the middle there is some sort of star there, and then you can see half of the star here and half of the star here. I hope you can see my mouse here moving. And again, it's not because they were trying to impress the instructor by leaving a star in the middle. It's because they couldn't figure it out, the geometry of these areas. So at the end, those were the parts we couldn't solve. So they were left open. So yeah, I'm going to, that is the last part, the last slide of the first part. I'm going to leave it there because I'm going to retake after I finish the second part. So I'm going to go now to something is related with introducing seismic design principles to architecture students. So in 2014, I was asked to come here to Yaşar University to work in some sort of experience, I would call it in that way, whose aim was to integrate seismic design principles in an architecture studio. And here's the problem when you try to do that. There is a lot of knowledge, let's say, on the technical side of how to introduce seismic design principles. The guide I'm showing there to the left is one of many. And the engineers have made really easy for architects to understand and to follow these principles. So the problem is not the lack of knowledge. The problem is not the lack of manuals or handbooks or the lack of, let's say, guidance. The problem is a different one. The problem is that the principles behind these, let's say, earthquake-resistant buildings, which is some of them can be seen here in this A, B, C. A is what are you showing there? You can ask, I would say, well, that the structural elements should be symmetrical, that you should try to avoid random openings like this one. This is wrong because you're cutting the connection between the slab and the structural element by a staircase. And the C is showing in the front is showing a mistake, which is discontinuity of the vertical structural element, whereas it should be like the one at the back, which is continuous. So that is the problem. The problem is that these seismic design principles imply symmetry, imply regularity, continuity, orthogonality, which are not necessarily things that architects do not like, but the architects, what they want, especially students, they want freedom. They don't want to be told to design things that are symmetrical. They don't want to be told to do things that are orthogonal. They don't want continuity just because it's imposed. They want freedom of and for design. So that was the underlying problem. The problem was not the lack of knowledge. The problem is how you introduce that one. Now, I have to say that my motivation to come here, it was driven by this type of approaches. This is a building that is in Chile, and it's, as you can say, is a mid-rise office building. And in Chile is an earthquake-prone country, so we have to design earthquake-resistant buildings. So the problem, if you look at the plan here, is that as represented by these two very thick black lines, is that the back of the building, in the image you're looking, let's say the facade, if we can look at the back from the other side of the building, you will see that there are two huge walls, which are represented by these thick walls here, thick lines. Now, I don't want to go really deep into the technical part, but that is going to provoke a huge problem of torsion with the building because these walls represent stiffness, lateral stiffness. So when the earthquake comes, these thick walls are going to take most of the resistance. So the building is going to start twisting. There will be a lot of torsion. So the question in this case, or the logical solution from the, let's say, seismic design perspective, is to balance this distribution. So take this thick line that is on one side and put it on the other side. So if this is one thick line, well, we should maybe take half and put it here on the other side, and then half of this one and put it here. In that way, you will have equal stiffness, but now distributed in the perimeter of the building. Of course, if we do that, then that means we are going to have huge walls on the facade, and the architects didn't want that. So how can we solve this one? Where the architects work together with the engineers, they come up with this solution, which is some sort of brace, namely diagonal, in the facade in such a way that the stiffness of these two facades can be very close to this one by using a different element. And at the same time, there is some degree of transparency, so the offices behind are not really closed. Now, again, and there is, of course, certain level of understanding in the distribution of forces, but at the same time, there is a design intention, which I hope you can see. Now, again, you might like as architects, you might like or not this solution, but certainly it's a combination between architects and seismic engineers. But moreover, you can end up with things like this one. And again, I'm talking about what motivates me to try to combine seismic engineering with architecture. And you can say, well, I know that work. That is Toyo Ito's store in Japan, which was inspired by the trees outside in the street. And I would say, yes, that's true, because Toyo Ito kind of make drawings of these trees, like that is in the picture, and then he liked this kind of interwoven of the branches. So he created this architecture of the building, like is kind of like branch going around. And you could say, yeah, that is pure architecture. There is no seismic engineering there. But I would say, in topology optimization, which is, let's say, a technique that allows you to distribute the material according to the loading you are going to have. If you take a rectangular surface and you put it vertical, and then you apply lateral forces, as it happens in an earthquake, or at least the simplification we make of it, then you're going to have a distribution for forces very close to this that I'm showing you now. So these three images in the upper part represent the optimal distribution of material if you have a set of lateral loading, which is very, in a simplified version, what happens in an earthquake. So here, on the contrary, you might think, is not only the, let's say, the design or the inspiration of the architect that drives the final form or the final configuration of the building, is a combination with the structural work. So there are more examples, of course, not so many, unfortunately. And these were the things that inspired me to say, okay, let's try this in the studio. There is hope if you want to combine architecture with seismic engineering. So we start the first year in 2014, and of course there are more results. But this was one of the results, which it was a problem for us because the students were scared. The students didn't want, after you introduce the seismic principle, the students do not want to leave from the safety of the boxes. They were making boxes everywhere. Some instructors, some colleagues were mocking me, and they were saying that you like boxes, that's why the students are making boxes. And so the problem is, again, we started to clash with this freedom. The students were saying, we don't have freedom to design because we have to follow these rules. So everything has to be walls and everything has to be orthogonal. And on the other hand, there was another problem, which is a problem that comes from the way we teach architecture. It's not necessarily a problem, but it became an issue. And it was related with the people who are working in let's say, in collaboration to teach architecture. And it's this one. Most of the architects have this idea that the structural principles, in this case seismic principles, should be introduced after we have a design idea, or let's say we have a shape, we have a configuration. So most of the architects, if you ask them, they think, okay, the idea or the proposal is going to come from an interaction between the program, the function, what is the building is going to be, understanding the site, context relationship, and of course, maybe some conceptual approach I have, and that is going to determine the design. And after I have an idea of the design, I introduce the structural principles. Now, let's say, what is the problem with that? Because that is one approach. The problem with that is that when you follow this logic, the earthquake-resistant principles are going to clash with the design ideas because they are not going to match. They will never match. So the only problem you're going to have there, the only thing you're going to obtain with that approach is a conflict. It's a conflict between, let's say, seismic design principles and design idea. And you have to compromise. And compromise means that either you deny or you neglect earthquake principles, or you neglect the design idea. And because the students were in panic, they neglect the design ideas, and then they start doing things like boxes. So how do we solve this problem? Well, we solve this problem by introducing these principles at the beginning in the conceptualization of the design as a form, as a shape, as a configuration. So we not only have the program, we have the site, we introduce the structural principles, and we add some conceptual approaches to that to merge them together and then come up with a design idea. So then after that, I started to think how we're going to do this. So I thought, well, we need a method. We need a method that we need to apply to the studio in such a way that these things can be actually implemented. So the plot that you see here is a very, let's say, idealistic teaching learning process in the studio. The vertical axis represent a design complexity, any type of design complexity. So in the studios, we usually go for a kind of low complexity, or let's say large scale if you want, and then we go to a smaller scale with higher complexity. You are expected, I guess most of the people in the audience, if not all, is being in this process of being design process. So you know that you start with overall things, and then you start going deeper, either in the design or the scale, and then in design complexity or the complexity of the variables involved becomes larger, right? And on the horizontal bar, you have the weeks, the timeline. So you, in the studio, you usually have a series of tasks that has to be developed in certain week, a certain time, for example, weeks, and you are expected to increase this design complexity that can be translated also in complexity and knowledge. Again, this is ideal because we move from low, starting the first week, to medium or to advanced in the second, and so on and so forth. So we keep increasing until we finish. That, of course, in the practice never happens, because after you go to the first step, let's say the task is B, usually you have to repeat this task in a studio. I'm talking about, not necessarily as an average, not necessarily individually. Why? Because some students go faster, some students are a little bit slower, or some students want to spend more time in certain aspect, or the students want to work more on this aspect. So it's never uniform. The process, the teacher learning process in a design studio is always very heterogeneous. So at the end, you always ended up repeating tasks in one way or another. So the advantage of doing that is that the students that are a little bit behind can catch up, and the students who are a little bit more advanced can improve their response. So that is I would say this is more common, let's say, pattern in this overall simplification, of course, because the reality of the studio is much more complex than the one depicted here in these very simplified schemes. But I hope you can follow my train of thoughts in this case. So then you move to C, and then you repeat again C, and then you finally reach D. So you reach the same design complexity like this one, but you require a little bit more time in the negative side. And the positive side is that you have iterations which allow, again, some students to catch up and some students to develop a little bit further. And I started to think, what method or how can we improve this one? What type of method should apply? And I remember a method that we used when we were climbing. I used to climb mountains. I don't do it anymore, but I climbed mountains for almost, I say, more than 10 years. I didn't climb the Everest. If you are looking at this, I just use the Everest because I think it's the easiest one to, and everyone knows it, so it's easy as a reference. Unfortunately, I never climbed the Everest. But if you look at here, I mean, if you look at this very interesting image, which I remember is from the National Geographic, here you can see the summit is almost 8,600 meters, and then you can see here at the bottom the Camp 1, which is 5,000 meters. So there are roughly 3,000 meters, a little bit more than 3,000 meters difference. Now, As you might know, when you go higher in the altitude, the amount of oxygen in the atmosphere reduces drastically. And that means that you cannot just, I mean, apart from the physical effort, you cannot just climb up. You need to make your body acclimatize. You need to give time to your body to get used to this. So instead of going, let's say, if you look at here, there is camp 1, 2, 3, 4. Instead of jumping from one to the other, what we do is we usually go higher. So we go from camp 1 to the number 3. You say, well, what happened with the number 2? Well, we come back and we sleep at the number 2. And then instead of going directly to the camp 3, we go to 4, and then we rest in camp 3. And you can say, well, that sounds a little bit stupid. Why are you doing that? Well, because when you move higher, you expose your body to more extreme environmental conditions, but then you go down again to an area. Why you go down? Because now you're going to sleep at the level when there is more oxygen. So it's going to be slightly better than the place you were. And that, let's say, psychological and physiological change makes a lot for speeding up your process of adaptation. Again, in my country, we don't have such mountains like 8,000, but we have a lot of mountains that are over 6,000 meters. So what we actually did is something like you can see here. Usually the base camp is 3,500 meters. So first you go 1,000 meters, 1 kilometer high. This is the normal. And then you go half kilometer down. So you rest there. Then the next day you go up again, and then you go down again. And then the last day you go to the summit. So what is happening here is this technique is called sawtooth because it's more or less the shape you ended up with when you draw this system. When you explain it to someone and you do it by hand, you ended up with this sawtooth. So I thought we can apply the same system here. Why? Because I thought, well, we are entering an area that is complicated for the student, that implies a very rare environment, a very strange environment for the student. So instead of going slow and try to introduce these principles little by little, we should go very drastically and very fast to this one and force them to do more and to try to understand more and then come back to a safer place and then do the same thing. So these sort of incursions is what you see here. So in the previous one, we went from A to B. In the case of the sawtooth, we go from A to C. We skip B, but then we come back to B. And then again, we go to D and C and D. So the iterations are at the end. When you already have all the experience, when you come back the second time, you have been already there, and then you're going to be in an easy place. Of course, this is very much conceptual, and I'm going to show you some of the results of this practical application. So we apply this in 2 consecutive studios. 2015, we work in Cadifecale. First, this is 1 semester, so each of these projects took 7 weeks. First, we develop a school, and we address the problem of configuration. And then the second project was a house, and we address, let's say, a problem of detailing. All this was done in a teamwork. There was no individual work here. There were 56 students. I'm mentioning this because this is important for comparison with the next case. There were 3 architects as a let's say, the team. There was one architect and structural engineer, and there was a structural engineer that came and joined us in the house project. This engineer, by the way, is Andrew Charlson, who is the author of a seismic design for architects. He's a professor from New Zealand, and he very kindly came and helped us in the second part of the implementation. In the studio, in the next studio, we changed the approach for reasons I'm going to explain later, and we use again a school, but we use a fictional site. There was no real site, and again, it was a teamwork. In this case, the number increased drastically because we had that problem where many students from some universities were closed, so we receive a lot of students. So the number went to the roof. So we were 5 architects plus 1 architect slash structural engineer. And then in the second project, the last 7 weeks, we work in Manisa, and we develop we call it center, the world cultural centers, educational center, and so on. So this is the first sawtooth implementation for the first one. This is the school in Carifecale. We introduce the idea of having some workshops. Something you are not going to see here, and this is very important, there are no desk critics. We didn't talk, we didn't sit there to talk with the students. And that it was very drastic, and the students were really much, let's say, skeptical. Well, not only the students, some of my colleagues were also very skeptical about this approach. So the approach here is that they make very quickly, you see the weeks here are in 7 weeks, we have to come up with a project. So each week there was a workshop and a delivery. So in the workshop, we select the best works, and then we give feedback to everyone based on this work, and then they have to prepare the delivery. And it was like this. It was a high-speed train. It was a workshop delivery, workshop delivery, workshop delivery at different scale. Here you can see the scale of, and then we were introducing different subjects. So, for example, this is the first workshop, which is called Site Program Location, in which the colors represent, the cubes with colors represent different functions. So the students have to come up with an organization. Of course, this has several problems. There was a lot of confusion here, but there were also positive aspects. In one of the positive aspects of this approach is that the student has to use something that is called prior knowledge, which means when you do this very quick exercise, the students are not going to learn anything, but they have to use all the knowledge they have. And when they use all the knowledge they have and they finish that knowledge, they cannot use more because they are using the knowledge they got in the second and the first year, because, sorry, this was a third year studio, I should mention that. And then from now on, everything else you add in the studio is new knowledge. When you start very slow, when you make a studio and you start very slow and you start, oh, let's make site analysis and whatever, the students not necessarily are learning anything new because they are using something they already know. But when you force them to come up with a proposal like this, in the first week, they exhaust all the knowledge they have. So everything else you add after that is going to be new knowledge. So they learn a lot. And I'm going to prove that. So this was the second or third workshop, which is it turned to be one of the most successful in this approach, and actually the essential one, which is a workshop where they take lateral resistance system. Oh, what do you mean with that? For example, this is a brace frame. Well, there are a lot of brace frames. There at the back, you can see some shear walls, and then there were some moment resistant frames here in the other picture here in the back. And they have to produce let's say, a configuration dealing with an interior space, let's say, a longitudinal space. So this was basically a combination of the first year in which they prepare spatial organizations, but using elements, structural elements. And again, to me, that was the combination. And in some cases, the project were triggered here. The projects as an idea, especially in the house project, they were triggered in this workshop. Now, quickly, I don't want to go really into detail, but quickly, the result of this first experience were still, I would say, a little bit disappointing in the sense that we're still in the boxy level. There were some tries or attempts to break this, but the students were still pretty much scared about moving out of the box. So then we prepared the house project. More or less, the scheme was exactly the same, as you can see, very intense. A workshop here in the delivery in the same week, workshop delivery. There was, again, no desk critics. what we did was, again, selecting the best projects, and we were talking to everyone, and that was it. And then they have to work with that knowledge and come back. It was very intensive. The students were very, very much tired. And here we, in the 5th week, we introduced the problem of the node, which is the connection detail, really, really close, which is what you see here. Well, what you see to the left, this let's say model is a model of a house displaying the structural system. This student was working with steel, and after that we jump directly from this scale to the connection detail, which was 1 to 5 or 1 to 2. So here is Andrew, by the way. Andrew is the person who is to the left. Is professor, as I said, from New Zealand, Andrew Charlson. There is a student in the middle, and I'm talking about, I don't remember what, something with the notes. So they were using different colors to explain different materials and different combinations. So this was very sharp. We were going very quickly into the structure, very quickly into the detail, and then go back to the architectural approach. So this is one of the results. There were, let's say, in this case, there were better solutions, or let's say more inspiring solutions. However, we think, and when I say we, I think Andrew and I think that this was the effect of reducing the scale, because when you have a small scale, the structural problem becomes less important, as I said before, because of this gravity issue. The larger the scale of a project, the larger the structural problem is. So there was an interesting approach here, for example, in this house that we like very much. I mean, the structure was finally part of the language of the house, and there was a certainly technical knowledge. That's what I said before. The students really learn with this principle. They really acquire knowledge with this sawtooth method. But of course, the students were all crying, and there was a lot of, burn out students because of this system. This is a system where there is no pause, there is no breathing time. Everyone was working. There was a delivery every week in the studio. So it's very intense, and for the studio was for the students was very, very demanding. So the year after, because then there was a break here. I mean, there was the other studio, so we came back.
Mauricio, sorry, would
yeah.
you like to have a little break at some point? Because the screen, the screen time makes people kind of tired and they need a break after a while.
Yes, I am planning to do this, if you don't mind. I would like to finish this part and give a break so I can get this some. Yeah.
Okay.
Yeah.
Sorry for that. Yeah.
No problem. No problem. I understand. I'm aware of the approach, but on purpose I'm trying to extend a little bit so I can at least conclude with this. Maybe the other part can be much more shallow. So so we entered this second year, and here you can see that we introduced the desk critics at the end. We introduced only one, and we introduce also, we make some variations here, but basically was the same. I remind you that this was a project that had no site. I mean, it was a made up site. And then we went from one workshop to the other with delivery. So it was also very, very intense. And before the final delivery, we introduced a time where students can talk. So this is, again, we use the same principle. We use color boxes. Some instructor thought at that time that the reason why we were having boxes, it was at the beginning immediately convey a box-wise project. In other words, some instructors thought that because we were using boxes at the beginning, the students couldn't move away from the boxes, and then they ended up making boxes. That is partially true, or in another way to say is to say that some students couldn't move, but some of the students managed to do that. So again, we did that, but again, we ended up with very much projects in a box way. Of course, with, let's say, all of them or most of them fulfilling the requirements of the design, let's say, seismic design resistant, but still, if you allow me, there was no much architecture that we can deal with. So, and again, some instructors say that that is related with the first exercise. So in the last project, in the second project, which is the last time we did this sawtooth, we make some radical changes. This is the most different from the other three. We introduced the desk critics right after the workshop. That was the first change. And we realized, and this was a complaint, because by the way, we were making surveys and we were talking with the students after the studios to understand how they perceive this. And one of the main critiques we received is that they felt that there was no time to think, because this was a machine. There was a train that was, they were doing a workshop delivery. They felt that there was no time for them to really reflect. That was the word we were using, reflect on what they have done wrong, what they have done right, and to apply that understanding in the next delivery. So we introduced the critics here as a way to give them time to think better. So and the second change that we did here is, if you look, we put all the workshops in the half of the studio, and the half of the project. So there were 4 workshops, there were critics, but there were no delivery. And then we put all the deliveries at the end. So the students were making the workshops, were talking about what they did in the workshops, and then at the end we put the deliveries. And this was also a very, very drastic change. We were working at 1 to 200, and then we jumped to the detail connection. And that was very, very drastic. There were a lot of, I would say, damage in doing that. But at the end, it turned out to be very much beneficial, because the students, once they were there and they came back, they had some knowledge about the structures and some about the construction that they use in the late deliveries. So again, there was a problem here, and that is why I'm showing these images. There was a problem we realized very quick when we were analyzing the site, that the students were not really understanding the site, and then there was a very slopey place. So someone who was not me, that is why I'm saying someone, I don't remember who, was one of the other instructors, came up with this idea of making a kind of conceptual model of the site. And this conceptual model could be made out of a waste material. So that is why you see this cigarette box here and this one. So that was fun, but at the same time, it triggered again some architectural ideas that later became the project. And I'm showing you this model on purpose, because I'm going to show you something later when I finish this part. And again, as I said before, we went very quickly to the detail. That was very, very dramatic step. At the back, you can see 2 of the part-time instructors, Meliha and Aisu. They were collaborating in the studio when we were doing this, because the students were working at 2 scales or 3 scales at the same time. They were working on the site, they were working on the configuration, they were working on the structural details, construction details. And but at this point, I remember something that Frank Gehry said in an interview once, and he said that he was showing a model of one of his works, and then he moved to another model that was a different scale. So the person who is interviewing him, asked, "Do you always make different models of the same project at different scales?" And Frank Gehry quickly replies, "Yes. You have to do that," he says, "because otherwise, if you only make one model of your project, you fall in love with that model, and then it becomes some sort of sculpture, and you keep improving it, not thinking on the work, on the architecture. You start improving it, thinking as an object. When you move from one scale to the other, you lost this perspective of being an object, and you start seeing the project." When I was doing this, when we were doing this, I didn't know that quotation, but it really fit really fits what we were doing here, which is this simultaneous work. And not surprisingly, this was the best. Let's say this studio had the best outcomes in this regard. There were freedom, there were interesting architectural proposals, but at the same time, there was knowledge. Remember, if you look at here to the right, you will see I think it's block wall or maybe bricks, and you see this very weird, let's say, teeth here. Well, this is a technique to make the wall be part of the masonry element be part of the wall. So this wall is structural and is working as a one thing, which is something I was discussing at the beginning. I was telling you at the beginning that if you connect the masonry with the frame, it becomes a structural element, which is what the students wanted here. And at the same time, there is this detail here supporting, allowing the masonry to have a opening, which is knowledge that comes from the building construction, and so on and so forth. So here you have a project that combines the three areas in one thing. So it was possible to do. And this is what I said to you at the beginning, that some projects are triggered by things that you're not expecting. When the students brought this model, we start talking about that it will be interesting that these lines somehow become the walls, shear walls that can help to resist the earthquake. And this is the final project. So there are walls here, and they have these. The walls are kind of representing the land and this dynamic movement of the slope, but at the same time they are working as a structural element. If there is any seismic engineer among you, you would say, yeah, but you have walls mostly in one direction. Yes, it's true. So we have to add very huge beams in the other direction in order to make some sort of frames, moment resistant frames in the other direction to balance this distribution. So I'm going to quickly go over the conclusions, which are not many, so then we can make a break. We make some interviews, we conduct some interviews, always after the studio was over. And from those interviews, we understand that the students were aware. They understood the reasons behind making two projects. Some of them said they took it in a very, let's say, I would say, philosophical approach. They say, well, in the first project, we made all the mistakes we had to make, and then we learned, and then we improve for the second project. And other people realized that in the first project we were targeting the configuration, whereas in the second we were trying like, okay, now you have the knowledge, try to make architecture out of it. Other thing we realized in talking with the students is that there is this let's say, confusion between structural design and seismic engineering design. And the final thing here is that even though they find, all of them found it very, very difficult, they thought, especially once the students graduate, when the students go into the professional area, they think that this work we did there was very worthwhile, that it was really, really important. And because they, in many ways, one is that doing these things and bringing these, let's say, real aspects to the projects gave them the feeling of professional life or the real practice that actually they found afterwards when they graduated. The students, whether the students increase their design, architectural design skills by introducing these principles is still a subject for debate. I think to some extent, yes, they increased when they were able to control and to manipulate this structural system with an architectural purpose. But on the other hand, some students still feel that all these principles are going to limit their design freedom. So that is always an open question. It's not really clear. Something that we learned from this, the application of this method is that this is a team-based effort. This is not let's say, a method, teaching method that can be given to individual work. It requires teamwork effort. And finally, we come up with some sort of ideal sawtooth method for, and we think that this is applicable to any studio, architecture studio, that is aiming to introduce technical knowledge in it. So we have a first stage that we call the exploration phase, in which you introduce workshops, either model or drawing based, and then you have a critic, you have a conversation with them. That the main goal with this critic is to give them time to reflect on what they have done in those workshops. So here in this first stage, there is no delivery. There is absolutely no delivery. And then you can go back to the beginning or close to the beginning and start working with these deliveries that becomes more complex as they grow in time. And this is when they integrate all that knowledge that was explored, was open, or was brought on the table here, they integrate it here in this second phase. So yeah, I think now it's been enough of me talking. I'm going to, well, I think we ran out of time, or not? No. Not really sure.
We have until 3:30. Yeah.
3:30. Okay, so let's make a how many minutes? Let's make a 10 minutes break, and then I'll come back with the last part of the presentation. So I'm going to continue, if it's okay.
Yes, great. Thank you.
Yes, Jen.
Okay. So, Gulsum, I have two more parts. I'm sure I'm not going to be able to show them both. The second part is a video, is a part of a video I want them to see. So what I was thinking is maybe I can give the link and explain what they could look at, and if they want later, they can check that part. So I will finish only this, let's say, the type of the lecture itself. So I need to share my screen. Okay. Yeah, I hope you can see. I'm going to quickly, because now I really have, I think, like 20 minutes or so. So I'm going to show you the last part of the work with the models in the spirit of bringing, let's say, new variables to this approach. So one is that in all the previous models I show you, the one with the Fuller and all these models that you saw, there was no function. We consciously deny the architectural effect of these works, and we only work them as objects. But in the late years, we've been working in structures or models, again at large scales, where there is a function. So this is a workshop that we made in Poland, and the idea was to create a water tank. But those water tank has the problem of the water container. So is an element that has to be it has to be designed in a resistant way, but at the same time, and the reason why you, in case you don't know, the reason why you have to elevate these tanks is because then you use the gravity to create pressure in the system, so you can actually bring the water to any place you want. So that was the idea, that was the workshop, but there was an additional problem, which was we want to make these water tanks for an area where there was an earthquake. That was the let's say the brief. we have an earthquake, there is a disaster, and we need to quickly assemble a water tank so we can fill it with water and then use the water to help the people there. And so this is a shaking model, shaking table model that where we were testing these models. And at the same time, there was another constraint which was very interesting, which is we had to design this water tower made out of paper tubes. So we, after some arguments between the students, and I was working with Peter Eichenram, which is a friend of mine. He's a mechanical engineer in Delft. So we quickly come up with an idea, all of us, students and us, and this was this hyperbolic paraboloid shape that you see there. And in order to build that, and please bear with me a little bit here, you have to connect two of the paper tubes you saw before, like this one, and then connect the other two like this one, so you can hold them in each hand because they were very, very light. Imagine it's just paper. And then at the top, we create some sort of join. So then you have this some sort of scissors element. So then, let's say to the right is number 3, to the left is number 1, and to the upper part is number 2. And the reason why I'm giving you these numbers is because I'm going to explain you how we could assemble. So again, number 1 here is the bottom of that tube. Number 3 is the right bottom of this one. And then 2 is actually where one person is going to stand, right? So this is how you stand there. And then another person comes and puts one tube here and the other leg here, and so on and so forth. One leg here and the other leg here and the other one here. So you ended up with a form that is like this one. And if you do it with orientation, this organization, you are going to end up with, let's say, scissors that are crossing at one point here. However, if you take the point 1 in the same position, but instead of putting it here, you move it in 180 degrees till here, and then you do the same thing with all the other people, then you have a double cross, which was what we actually wanted to do. So again, the difference between these is that the separation between, let's say, the legs in plane is 120 degrees or 180 degrees. Now, this is the theory of that, and this is the practice. In the middle, Peter is there, so he was guiding each of the students. So each student was holding these two legs that were connected at the top, and then everyone was moving them. And I'm taking the picture from the upper part because I'm making sure that the upper part is connected. So then when everything was in place, there was another person just screwing this and making the assembling part. And this was very quick. I don't want to go there very quick. Just a couple of things that are interesting for me to mention before I move to the next one is that Peter, as I said, he's a mechanical engineer, and here you can see these two line of crosses. That is one, and the other one is here, which is where it crosses. First, we put the tubes in such a position that we only have one cross. And Peter was like, okay, we did it. And all the students, plus me, we are architects. And we said, no, because it's just one. It's too simple. We want two crosses. So we need to try again. And then we tried the second way, which is increasing the angle. And then everyone had to move around. And then there was, imagine a huge mess of legs, arms, and actual human legs moving around while Peter was in the middle. And then we come up with this one, and all of us like it. So Peter, again, who is not an architect, but he's been around architects many years now, he said after that, he said to all of us, that was a moment I understand how the architect think, because to me it was obvious that it was okay in the first part, but you are looking for something else, and you are looking for something that has to do with design and not necessarily with the structure. And here to the right, you can see the tower after it was installed here in a kind of open area for drinks and eating here. And then again, you can see the two lines of crosses here that we're very proud of. Again, I'm going to go quickly. This is an exercise we made here in Izmir. At the beginning, of course, as always, we made a brainstorming. Someone proposed this HyPar thing, and not everyone was really convinced. The guy here in the middle is Jerzy Wodka. He is from Poland, from the Wrocław University of Science and Technology. He's a good friend of mine. And with Peter again, we were organizing this workshop, and Jerzy is the person who is the responsible of using these paper tubes over and over again. His expertise is in paper architecture, so he likes to work with these paper tubes, which pose a lot of problems for both of us, Peter and I. Here you see some of the students at Yaşar talking with Peter about possible connections, and to the right you see when we started assembling the first HyPar, we came up with an idea of building 3 of them. There were a lot of troubles, as always, and there was a lot of hard work here. You see us working at night. We had to figure out many things on the way, and then here you see when one of them was finally installed. Again, as you saw at the beginning many times, this is a very common topic or subject in my own, let's say, teacher experience, because we always make these HyPars over and over again, and I always feel fascinated by these geometries which create curves. As you see here, it looks like everything is curved, but at the end is made out of straight lines, which always have fascinated me. We have to come up with some last-minute solutions, because there was, of course, a lot of structural problems. We have never done a I'm going to show you a very funny video that Jerzy made about the process of assembling and how we transport them to the place. I'm sure you all know more or less where we are. In case you don't know, we have to transport this to the back there. It's not really far. Luckily, the structure was very light. So some people can easily take it. Again, as always, teamwork. This cannot be done with one person or two. You need always different people doing a lot of stuff in each workshop, and that is something I like about all these experiences, is that you need to improvise and you need to use creativity. The form, again, is very simple, and when you look at the computer or you draw it by yourself, you're going to see that it's not really much, it doesn't require much work to understand, but when you try to build it in a very simple one, there is so many work and so many things related with building construction, again, that are, of course, I would say challenging, but at the same time, they give you the sense of satisfaction when they finally are over. And this is the final work, very late on a Friday night, after 5 days of hard working. We ended up with this, which of course made everyone very happy. Then there was intense rain here, and of course, as I said, these were paper tubes, so we took care and we protect them with plastic, but at the end, because of the connections, because of the screws, we forgot to cover some of them, so the water went inside, and then we ended up with this type of connections, which at the end made the whole structure to be weakened, and we have to turn it down. In the last part, with this one I'm going to definitely finish, is the gate, which was an exercise again in the same spirit, building something at larger scale. In this case, the excuse was to make an urban intervention, an urban furniture, and the idea was to make a hybrid artifact in which we combine digital fabrication and, let's say, or traditional construction using these buttons. So in order to first introduce the subject of funicular shells, we made a very fun workshop in which we use candle wax that is melted. So you use these pieces of old fabric, and you pour these melted candles, and then when they are dry, of course, because it's candle wax, when they are dry, you can turn it upside down, and then you have these shapes as the one you see to the left. And then there was this very nice that it was white, like you see here. It was a white fabric, but we used red candles. Someone brought red candles, so when they combine, it appears this very interesting pink color. And because of the tips of the fabric were loose, then you have these very organic shapes. And all these things happen. You cannot plan them. You cannot foresee them. You cannot really draw them. Perhaps you can only see them after you make this crazy stuff, or you start doing this fooling around with materials and things. And again, that is something I really enjoy about making workshops. And in the terms of design, we made some sort of competition inside this was an elective course. So all the students proposed different, let's say, grid shells using funicular catenaries. And at the end was this one. The students, actually, I didn't choose anything. I think you choose. And they chose this one because it seemed to be easy to install, and it was kind of straightforward. It seemed, because it wasn't that easy. So then after that, we had to redesign this initial proposal, which is what you see there in the upper corner. In order to come up with a number of nodes we need something like 67 nodes, and we have to add some bars for providing extra, or actually providing stability to the structure. And we have to design each node. Each node was different, so there was some boundary constraint. We need the connector there, which is this box that some of the students design, and then you were free to do whatever you want. So the students start doing, some of them start doing kind of optimization approaches. Some of them make this potato thing that we call it potato, and this one, which is like just a ball there. I mean, there was not much creativity implied. And then we asked them to make holes just to reduce the amount of materials, because the problem was the printing time was consuming. So we divide the construction process in 3 parts. We first build the beam, and then the columns. By the way, we were 7 people making all this project, including me. I was working with the students, and this is what I meant before. Each of these nodes, which were 67, let's say 17, including the ones we did wrong. You have to consider that there are many faults, many mistakes in this process. So each node took around 20 hours, which if you multiply, you make the multiplication, implies a lot of work in here. So this was most of the time fixing the printers and the filament. And as I said, at the end, there were different type of nodes depending on the students' approach. Some of them like it more organic, and some of them just start combining stuff. There was a variety of and once the nodes were print. The other problem was, okay, so which node connect to what? Where is there? Then there was a huge there of knowing which bar these are going to be connected in which order, and so on and so forth. And here you can see the colors. The colors got nothing to do with any architectural intention. It's just about the PLA that was available at the time we purchased the PLA. And here we are cutting the bars. And then here there is this combination, knowing which bar connect with what. So there was first a trial to understand if everything was okay, and then we could actually start the assembling process. You see a lot of tapes and a lot of connections to know, again, what is the right way to connect. We made a lot of mistakes here. We broke some of the nodes in this process. Sorry, then was the beam, as I said before, and this one are the 2 columns, or the 2. This one is here, the other one is there. And then we did this division in order to make it able to transport it to the place. And then once it was installed, they realized about some structural problems. For example, here you see the cracks that appears in this connection, and there are two reasons for that. One, the main reason is if you look at here, the beam, this is working as the arch, but at the end is working as a beam. So that means there are tensile stresses occurring here more. And in the second part is related with the way the 3D print creates the node, because you can see here layer by layer. If you know about 3D printing, you know 3D printing is printed by layers. So here you can see the lines, and basically what the forces are doing is separating these original layers. So we had to print again this one with the different orientation, so the layers were in a different position, so this node could last longer, because after this we were requested to present this structure in the exhibition of the department that was a month after. So we had to think that this structure should last at least one more month. And finally, this is when it's installed. We also check what happened with we installed some cameras there to see the interaction between the interaction of the people with the structure. There was nothing much going on. Most of the people just simply passed underneath. They didn't care about what was this weird thing in the middle of the park in Bornova, by the way. There we count 16 people that kind of feel curious about the structure, and then they came and touch it or try to hang or do something. They were curious, and while we were installing, there were like 4 people that directly came to ask what is this or what are you doing. So and with this I'm going to finish. After all these experiences, I have come up with we are using different type of models to teach, or actually to learn about structures. The first one I call testing model. The intention is to show a predetermined behavior. As an instructor, I know what is the behavior of this truss beam, but it's good to make, because the students are going to see the behavior. So for example, you're going to see this very straight line here, the timber bar, which means it's working in tension, whereas you see the bending of the other brace, which means that is working in compression. So you can see those things and you can experience that. Again, it's a knowledge that I have as instructor, but I need to transfer to you. So this testing model helps in that regard. So this type of model, the testing models, they provide empirical knowledge to complement a theoretical of any kind, usually related with structural mechanics. And there are these typological models which are made, we do, to explain the logic or the rationale behind certain structural typologies. The best example is this one that explains the funicular shapes. These are the best models, like hanging chains for this one. And with why we use these models to provide knowledge about form-finding methods, to understand or to kind of test possible fabrications or construction. Like what are you going to do first, and so on and so forth. And also it provides skills for architectural design, as I said before, because you realize about things that later can become part of the architecture. And finally, we have the exploration models, which to some extent are the ones that I enjoy the most, which are built to experiment. And experiment, according to Wikipedia, is a procedure that we carry out in order to support, refute, or validate hypotheses. So an experiment should always rely on a procedure that is repeatable, that someone can repeat and get the same result. So for example, and this is from the same website, by the way, in Wikipedia, they show this experiment as this baby kissing himself in the mirror. And I'm showing some examples of a models we made in TU Delft that were the base for an architectural project whose aim was to be able to create sand dunes. So the student was asking himself, how can the shape create actual dunes? So we said, okay, let's make some models. Let's try different shapes and see how those different shapes can increase or decrease the possibility of forming a dune. So here at the bottom, you see 3 different shapes that this it was a Chinese student, was a master student, was developing. So he first put this shape here to understand how much this shape subjected to the wind in Scheveningen in the Netherlands is going to produce, and then another shape and another shape. So at the end, we realized that this was the shape, the first one, that is most likely to create this type of dunes, and that is the shape that at the end is kind of applied in this project. So one of the things, and that's why I like these type of models, is that you always ended up with unpredictable results and you follow unorthodox solutions, which again is, I think, is my own approach to many things in architecture. So I'm going to stop here. I'll be very happy to provide you with links to the you can check later. So I don't know if there is any question in the last minutes or something you would like to comment.
Ajam, I would like to ask a question.
Yes, please.
Ajam, first of all, the presentation was really good. The second was about the sawtooth method. My question is that will it be more, productive if we use sawtooth method of our design studio, the design subjects, because to have a more productive and to have a more creative idea. Because I really like the sawtooth, up and down. It would help us. What do you think?
I lost you. Probably my internet connection is a little bit slow. I lost you, but for a while. But I think I understood the. By the way, thank you for your comment at the beginning. I think this method, the sawtooth method, will work for any studio, architectural design studio, aiming introducing technical variables. So I don't think it will work if we only go around, let's say, design issues. But if you want to introduce any technical knowledge, not only structures, let's say, I don't know, energy performance of the buildings, or let's say building systems, or any subject that is quite technical in itself, I think will provide a good framework to do so. I don't know if that answers the question.
No, yeah, it does. But in terms of the technical subjects, although what I think is all architecture subjects are technical subjects. So how do we differentiate between that?
Oh yeah, well, what I call a technical subject is when you introduce a body of knowledge that requires, for example, to understand first the principles that are related with other disciplines. For example, if you're going to introduce any performance of buildings before introducing them in the architectural studio, right? It's not like you just say, oh, the hot air mass is going to go up and a cool one is going to go down. I mean, that is not knowledge. I mean, that is something we all know and it's very basic. I'm talking about a body of knowledge that requires some expert and some level of expertise in his own framework, and then you have to combine it with the framework that we use in design, which is this approach based on desk critiques and based on going from a lower degree of complexity to a higher degree of complexity. For example, in the specific case of engineering, you need a knowledge to understand seismic engineering. You need a knowledge based on physics and dynamics and structural mechanics. If you don't have and plus mathematical background, if you don't have that background, you can hardly understand some concepts that are coming or are related with seismic engineering. Or say, try to combine this. We have to find interfaces that are going to take some of these principles and their applicability on architectural design. And that is what I think you need a method. In this case, I'm proposing this method. So again, I don't think this always happens in an architecture studio. Okay, you talk about structures, sure. You talk about energy performance, sure. You talk about orientation, you talk about many things, but it doesn't mean that you are actually incorporating technical knowledge into them. I'm talking about, again, incorporating a body of knowledge that you can not only, let's say, influence the design, but also you can prove that the design you are proposing, architectural design, is going to produce the effect or is going to have the physical outcome you are aiming. Again, a knowledge, what I call technical knowledge.
Thank you, Jam. I think I got the answer.
Thank you very much. Thank you for your answer, for your question. Is there any other question?
Thank you very much, Mauricio. That was a very explanatory and informative talk. I'm sure they have an understanding now what they are getting into if they work in this area, which is great. So thank you so much for your contribution.
Thank you very much for the invitation. Yes, I'm open outside the to this subject. Thank you very much for the invitation.